Alrighty, welcome everybody to today's physics colloquium. We have a very exciting talk and a great speaker lined up. Just before we get started on that, a reminder, today's the PMA Fall Gathering right after the colloquium, so stick around, it will happen right in front of Bridge on the lawn. So as you can see from the title of today's talk, we have an expert today in the microscopic nature of dark matter, Ben Safdi from the University of Berkeley. Ben did his undergrad at the University of Colorado at Boulder, followed by a stay at the University of Cambridge, where he did a Master's of Advanced Study as a Churchill Scholar. Then he did his PhD under Igor Klebanov in Princeton in 2014. He was a Pappalardo Fellow at MIT, before then starting out at the University of Michigan at Ann Arbor, where he stayed for a little while, then moved on to Lawrence Berkeley Lab, and then to the University of California at Berkeley, where he's been ever since. He's received many accolades and honors, including the Sloan Fellowship, the Early Career Award of the Department of Energy, and the IUPAP Young Scientist Prize for his work. Ben works, very broadly speaking, on dark matter searches, both theoretical as well as proposing instruments for including also astronomical data. Ben has worked as a founding member of the Abracadabra collaboration. He'll tell you more about the things that he's been up to, including searches for Axion-induced GRBs from galactic sources, where he's been even thinking about, what kind of satellites you need to detect that. And so I hand it over to Ben to tell us about all the exciting things on his mind.
Thank you.
All right, let's give you that.
Thanks a lot for the introduction. I need to apologize first. Can everyone hear me? Is this working? Okay. I seem to have lost my voice, so bear with me, and I will try my best. So it's great to be here at Caltech. It's great to see many familiar faces and to meet new people. It's really not that far away here in the Bay Area, and it's great to have these local connections within California. So today I want to tell you about the search for Axion dark matter. First, though, let's talk about non-dark matter. Let's talk about ordinary matter. I don't know about you guys, but this is not what the night sky looks like up in Berkeley. But hopefully you've all had the experience of going somewhere, maybe here out to Joshua Tree, and looked up at night and seen some beautiful scene like this one. In fact, looking at stars is one of the reasons that I got into science in the first place. Just found it was fascinating looking up at the night sky. But one thing that I now appreciate, that I didn't appreciate as a child, is that when you look up at the night sky, almost everything you see, we know what it is. These aren't mysterious objects. These are mostly stars. And I want to distinguish, though, between understanding what something is and understanding where something is. So as humans, for tens of thousands of years, we've been documenting where stars are in the sky. In fact, these cave paintings are now thought to be depicting stars, constellations that were visible at that time. But that doesn't mean that our ancestors understood what they were looking at. It wasn't until very recently, in, say, the 1940s, that we actually understood what stars are. They're powered by nuclear fusion within their cores. So to draw an analogy with dark matter, we're still very much in this prehistory phase. For almost 100 years, we've known about the existence of dark matter, and we've been able to document where it is on the sky. But the big outstanding question in my mind is, what is this stuff? What is the microscopic nature of dark matter? So this is a picture of a galaxy. This is not the visible part of the galaxy. This is the dark matter in the galaxy. This is also not a real picture. This is a snapshot of a simulation. But it's showing you what we expect, what we know galaxies look like in terms of the dark matter content. So most of galaxies, like our own Milky Way, are in fact made of dark matter. We know this from data. The visible part of the galaxy, both by mass and size, is just a tiny thing in the middle. And galaxies like our own Milky Way are surrounded by all of this beautiful structure. And the goal of my research and the goal of this talk today is to unveil the origin of the structure. How did it come to be, and what is all of this stuff? What is the microscopic nature of the dark matter that we see in astrophysics? In particular, what is dark matter at a particle level? And how does it interact with the fundamental particles of nature, that we know and love, like the electron, the Higgs boson, the photon, and so forth. So when we start asking questions like this about the microscopic nature of dark matter, it's fascinating how little we know. Let's just focus on one aspect of dark matter, which is the mass of this dark matter candidate. Its mass, when we talk about particle dark matter, can span about 50 orders of magnitude. And we have absolutely no idea where dark matter lies within this parameter space. On the lower end, the quantum wavelength of the dark matter is the size of galaxies. And dark matter can't be any less massive, because then the quantum wavelength would be so large, it wouldn't be able to form the structures on smaller scales that we know exist, like galaxies, and that sets a constraint. On the high end, your dark matter would collapse into a black hole. Maybe that's not too bad. You're willing to accept that. And then you can go up another 40 or so orders of magnitude, somewhere over here, and talk about black hole dark matter. And that's perfectly fine. So in fact, from data, the mass of dark matter is constrained pretty well to about 90 orders of magnitude. So we don't know much when we talk about the microscopic nature of dark matter, which is part of the reason that I think this field is so fascinating, because there exists an answer to this question. But that doesn't mean we don't have ideas. So you can see some of these ideas for what axions might be percolating up in this mass range. The one you might be most familiar with is WIMPs. These get historically the most attention. But today I'm going to focus on another motivated dark matter candidate called the Axion, and I'll try to explain why this particle is motivated and what we're doing to look for it today. So the timeline for the Axion, and also roughly the outline of this talk, is the following. So axions were first introduced to explain a problem called the strong CP problem. I'll explain this problem to you. It was then realized a few years later that if axions exist, they could also be the dark matter of our universe. I'll explain that to you. But then I'll focus mostly on the experimental effort today and what we're doing to try to discover if these particles exist in nature. So let's start with the strong CP problem, which I will refer to it by something less mysterious, the neutron electric dipole moment puzzle. So first, let's understand why there is not a similar puzzle with water. So water is charge neutral, but it has a charge asymmetry, and that charge asymmetry induces an electric dipole moment, which points in the direction of that charge asymmetry. What does that mean? If we put water in an electric field, it will precess. We're all familiar with this. So we can estimate the magnitude of this electric dipole moment. The magnitude is given by the amount of charge which is separated, one electric charge, times the distance of separation, about 0.1 nanometers, and we estimate 10 to the minus 8 e centimeters. You compare this to data, and you're right within a factor of 2. Pretty good. Now let's zoom in. On our nucleus, we have protons and neutrons. I don't want to do this with the proton because it's charged, and I don't want it to go zip off in my electric field, so let's do the neutron. The neutron looks a whole lot like water. It's composed of charged constituents, which are quarks, but it's charge neutral. So you might think that there's an electric dipole moment, which points in the direction of that charge asymmetry, which would cause the neutron to precess in the presence of an electric field. More precisely, there's a fundamental parameter of nature which controls the magnitude of this neutron electric dipole moment. That fundamental parameter of nature is called theta. What is the fundamental parameter of nature? It's something like the electron mass. It's just a fixed value of our universe, which cannot evolve. You can think of it roughly. This is an analogy. This analogy will break if you push it too hard. But you can think of theta roughly as describing the angle between the quarks within the neutron. If theta is 0, there is no neutron electric dipole moment because there's no preferred direction for that arrow to point. Everything is on a line. Theta is an angle. It takes values from 0 to 2 pi. And only if it's 0 do you get this vanishing electric dipole moment. So in the generic case where theta is non-zero, you have a neutron electric dipole moment, and your neutron precesses in the presence of an electric field. If theta is identically 0, everything is in a line, and your neutron does not precess in the presence of an electric field. So let's try to make this a bit more quantitative by estimating the magnitude of the neutron electric dipole moment. So the amount of charge separated is, again, 1 electric charge. The distance of separation is about a femtometer. You multiply those together, you get 10 to the minus 13 centimeters. But we know this should go to 0 as theta goes to 0. And so if you do a calculation for small theta, this is the result. It's smaller than our naive estimate by a few orders of magnitude. That comes just from 2's and pi's being in the denominator, and some of them are squared. There's nothing special going on. Those are just trivial factors which make up that difference. The confusing thing is data. No neutron electric dipole moment has ever been measured, and the upper limit is 10 orders of magnitude smaller than the naive theory calculation. What does this mean? Well, theta is an angle. Take values from minus pi to pi, and we know that we live in a universe where theta is at least 1 part in 10 billion away from 0. And the question is why? If I randomly create a universe, I randomly draw a value of theta, that one's not consistent with our universe. So I do it again. This one's also not consistent with our universe. And we need to do this at least 10 billion times to find a version which looks remotely like the universe that we live in. This is an example of a fine-tuning problem. A parameter in nature, a fundamental parameter, appears to be fine-tuned. And in particle physics, fine-tuning problems are also often a hint that something deeper is going on that we just don't understand. But it's a hint of physics that explains why that apparent fine-tuning happens. In the late 1970s, these very smart people up here proposed a possible dynamical explanation. What they noticed is that when we randomly draw a value of theta, the neutron really wants to push it down to 0. The neutron would be in a lower energy field configuration if theta was 0. So it's trying to push theta to 0, but it can't. It's a fundamental parameter of nature. It doesn't make sense for it to evolve dynamically. So what did they do? They promoted it to a dynamical field, which is the Axion field. Now the Axion is dynamical, and it can minimize its potential, and at the minimum of its potential, there is no neutron electric dipole moment. That is, we've made that angular variable describing the angles between the quarks dynamical, so the quarks can just relax to their lowest energy configuration, and in that configuration, there is no neutron electric dipole moment. But in doing so, we've introduced a new particle of nature, a new field of nature, a new light field, and that field is the Axion. So the picture that emerges from the late 1970s is that perhaps neutrons are not just quarks and gluons, perhaps they also have these axions bound up inside of them, whose role it is to cancel the neutron electric dipole moment. Let me take one slide, 1.5 slides, to describe this at a slightly more technical level. But the words that I'm going to say are the same words that I just said, but I'm going to frame them more precisely in the language of quantum field theory. So in the language of quantum field theory, the neutron electric dipole moment is due to this term, which could have appeared in the QCD Lagrangian, where G here is the QCD field strength. That would generate a neutron electric dipole moment proportional to this theta parameter. The Axion solution is to promote theta to a dynamical field, which is the Axion field. The Axion field is born in some sense, which I will describe to you in a few slides, at an energy scale of order Fa. Fa, you should think of as some very high scale. So here I'm keeping track of the cosmological history of our universe. So some very high scale, which could be the gut scale, 10 to the 16 GeV. The Axion is created. At lower energies, around the QCD confinement scale, QCD generates the potential for the Axion. Now when the Axion minimizes its potential, there is no neutron electric dipole moment. This is the same picture that I just described to you, but said slightly more precisely. The Axion is defined through its coupling to QCD, to gluons. But below the scale of QCD confinement, the Axion mixes with the neutral pion, and that induces a coupling to electromagnetism, in particular a coupling to E dot B, where E and B are electric and magnetic fields. This will be the most important operator in this talk, because what it allows for is for an incoming Axion wave to hit an external magnetic field, and then to convert into a photon. Think of this as a Hamiltonian term in the presence of a static magnetic field. Then this just describes a mixing between the Axion and one polarization state of the photon. And this, in practice, is the term that we usually use both in the laboratory and in astrophysics to try to detect axions. So I'll return to this term later on in this talk. But for now, let's also notice that if you expand out this potential, you find that there's a mass term for the Axion. The mass is inversely proportional to the decay constant. It's very predictive. If you put it in the gut scale, 10 to the 16 GeV, you get a mass for the Axion on the order of a nano-eV. This formula should look familiar to you. It's the same formula you see in the seesaw mechanism. Indeed, it can be the same high scale, say the gut scale, which explains the small neutrino masses on the order of tens of millieV and the axion mass. But then why is the axion so much less massive than the neutrinos? It's less massive because in this case it's the electroweak scale which enters into the numerator. And in this case it's the QCD confinement scale which enters into the numerator. But it's the same high energy scale which could be driving both of their masses to be very small. So I've been talking about energy scales, so let me just take a step back to make sure everyone is on the same page and to review energy scales in fundamental particle physics. So the lowest mass but massive particle that we know about, these are the neutrinos with masses on the order of tens of millieV. Going up in mass, we hit the electron, the proton, all the way up to the most massive known particle, the top quark, with a mass of around 173 GeV. This is the highest energy scale that we know of for sure in physics. But we expect, or there's indirect evidence to suggest, that all of the forces unify into the grand unified force at an energy scale, which I'll call the gut scale, around 10 to the 16 GeV. And there are reasons to suspect that these forces unify with gravity at the scale of quantum gravity, the Planck scale, around 10 to the 19 GeV. But all of these forces in orange are speculative, all these energy scales. The axion, if it exists, is generated, it is born, and I'll tell you what I mean by born. It is born by physics at very high energies. For example, it could be born at energy scales all the way up here. But it has a very small mass. So how can physics at a very high energy scale give rise to very light particles? The answer is symmetries. Symmetries which are present at high energies drive the axion to have a small mass. So let me give two examples of how physics at high energy scales can give rise to ultralight particles. The first is when the axion arises as the Goldstone boson of a spontaneously broken symmetry. So if you haven't seen spontaneous symmetry breaking, here's a very simplified version of it. Let's imagine a complex scalar field, phi, which is governed by the following potential. We want to find the ground state of this system. There's a degenerate circle of ground states. Everything at the bottom of this potential has the same energy. So if we think about the modes that we have, and for this system, there's two types of modes. There's the radial mode, which corresponds to going up the side of this potential. That requires a lot of energy. If we have a ball, we have to push the ball up that side. And then if that side is very steep, then that's going to require a lot of energy to excite. On the other hand, there's a massless mode. This mode is called the Goldstone mode. And the Goldstone mode corresponds to going around in the circle. Since it's exactly flat, by symmetry, it requires no energy to push the ball in that direction. So this corresponds to a massless mode. So the axion can be realized this way as the Goldstone mode, or pseudo-Goldstone mode, of a spontaneously broken symmetry. And I'll return to that idea later on. But let me give one additional way how symmetries can give rise to axions. This is the way that also provides an additional piece of theoretical motivation to think about axions, which is in the context of string theory. So it turns out that string theory generically predicts axions. That does not mean that the QCD axion is a definitive prediction of string theory. That would be too strong. But what is true is that string theory provides all of the ingredients that you need to have an axion. And oftentimes, you do have a good enough axion to explain the strong CP problem. So why is this? What are the crucial ingredients of string theory that give rise to axions? So let me explain this by a simplified example. String theory has two crucial ingredients. It has extra dimensions and it has gauge fields. So let's think of the simplest case of an extra dimension in a gauge field. Let me take an abelian gauge field. This is something like electromagnetism, but it extends to 5 dimensions. So I have AM here, where M goes from 0, 1, 2, 3, Minkowski space, and also some 5th dimension. But I'm going to compactify that 5th dimension on a circle of radius r. So you can think of this as the vector potential of that abelian force, for example, of electromagnetism. So if the m is equal to mu is equal to 0, 1, 2, 3, then this am, upon dimensional reduction of the theory on that circle, just descends to electromagnetism in 4 dimensions. But A5, when m is in the 5th direction, this component, or more precisely, the integral of this component around the circle, the zero mode, becomes precisely an axion in 5 dimensions. And the decay constant of that axion, this parameter characterizing when the axion is born, is just set by the inverse size of that circle. So you can keep this picture in mind throughout this talk, and when I say an axion is born at some scale, you could think of that scale as either the scale associated with spontaneous symmetry breaking, or the scale at which you go through this compactification transition and you cross to energy scales below the size of this compactified extra dimension. So the fact that string theory has these ingredients and produces axions is another strong motivation that we should be thinking about these particles in nature. So I now want to transition to talk more about the cosmology of axions. So to do so, let me just briefly get everyone up to speed on inflationary cosmology. So the standard picture of cosmology is that we have inflation, which happens at some early times, some exponential expansion of space, followed by a period of reheating. After this point, the universe is in some thermal state, it's cooling down. We have the QCD phase transition, form things like neutrons and protons. And then we have Big Bang nucleosynthesis, where we form light elements. This is the first epoch in history where we actually measure things precisely, which is why I'm coloring it in blue, temperature of around an MeV. The CMB decouples, and then eventually we get to today. So the axion, if it exists, would be born at some very high temperatures on the order of 10 to the 10, 10 to the 16 GeV. So now let me describe what happens when an axion is born, and how can axions go on to become the dark matter of our universe. So first, the language that I'll be using on the next few slides is very different from the language you're used to hearing if you're used to thinking about WEMP dark matter. And that's simply because the axion has a really, really small mass. In units where the proton mass is 1, this is roughly the order of magnitude of the axion mass. And what does that mean? What we measure in astrophysics is the amount of mass within some fixed volume. So as we make the mass of the individual particles smaller and smaller, we need more and more particles to make up that total mass. Axions are bosons. So as they become closer and closer, more tightly packed, their wave functions overlap, and we transition from being in the quantum regime to the classical regime. So when we talk about axion dark matter, we use the language of classical fields because that's the correct description to very good accuracy. So we have this new classical field that we need to include in the equations of motion in the early universe. This field is the axion field. Here I'm writing down its equations of motion, where dots are derivatives with respect to cosmic time. H here is Hubble parameter. If you're not used to thinking about it, and the epoch I care about is T squared, temperature squared over M Planck. Ma is the mass of the axion. I can solve this equation in real time at high temperatures. Because at high temperatures, Hubble dominates over the mass. Everything, so you can forget about this term, everything has a dot, which means its solution is simply A equals a constant. So if you put this in Mathematica and solve it, you'll see that at early times, the axion field is frozen at its so-called initial misalignment angle until Hubble drops to be of order of the mass. After this point, it looks like a damped harmonic oscillator. And indeed, after this point, the coherent fluctuations of the axion field behave like dark matter for astrophysical purposes. That doesn't mean that you get the correct abundance of dark matter. To determine whether or not you get the correct abundance of dark matter, you need to actually calculate the relic abundance. You need to do this picture precisely. And you'll see that you get the correct abundance of dark matter for an order 1 generic initial value of the axion field if the decay constant is on the order of 10 to 12 GeV. So this picks out a very special decay constant, and I'll return to that later on. But first, let me point out that I was not being completely truthful to you on the previous slide, because the picture that I just described is only true in one cosmological framework. It's only true if inflation happens after the axion is born. Because at the epoch of PQ symmetry breaking, when the axion is born, at the epoch when the axion is born, if I go from Hubble patch to Hubble patch, the initial value of the axion field cannot know about the initial value in some other disjoint Hubble patch. So they must be uncorrelated. But then what inflation does is it zooms us in and produces homogeneous initial conditions, such that after inflation, for all practical purposes, our universe has a single value, initial value of the axion field. which just corresponds to the value that we happen to inflate from. If we could travel space-like, extremely exponentially far away, we might discover a different patch of the universe which has a different abundance of dark matter determined by a different initial misalignment angle, but we can never access that patch. So it makes sense to talk about the equations of motion in the sense that I just described. But now let's imagine the more interesting case, where the axion is generated after inflation. Now we have Hubble patches, which are uncorrelated at early times with different initial values of the axion field. But all of those Hubble patches come in causal contact in the subsequent evolution of the universe. So now, how should we determine the abundance of dark matter today? The naive answer is you average over all possible initial misalignment angles, because all of these patches are coming in. But that would be too quick, because when I told you those equations of motion, I'd already linearized them. And it turns out that would be a bad thing to do in that case. I'd also, I had neglected spatial gradients. And clearly, if all of these patches come into causal contact, I cannot neglect spatial gradients. Most importantly, it turns out in the evolution, you develop topological defects known as axion strings, which require more care in order to understand. So this is a very nonlinear process. There's only so much progress that you can make analytically, but it's a very interesting question for the following reason. In the first scenario I described, the dark matter abundance depends on the initial misalignment angle, which we can never possibly know. In the second case, there's no free parameters. There should be a one-to-one mapping between the axion decay constant, which determines the axion mass. So a one-to-one mapping between the axion mass and the abundance of dark matter. We measure the abundance of dark matter. So we should be able to precisely compute the axion mass, which gives rise to the observed dark matter abundance. This is relevant for reasons I'll talk about at the end of my talk, which are the experiments that we're trying to build on Earth, the experiments we're trying to do in space to detect axions. If we know the mass of this particle, this would provide a huge increase in speed and our ability to detect axions. So why can't we tell you an answer? We can't tell you an answer because it's a computationally challenging problem. So it's analytically, you can only get so far. Afterwards, you have to do simulations. So my group does a lot of these simulations, and I want to describe to you some of our results on the next few slides. So what do we actually simulate? So let me describe the simpler version of this picture, where we're simulating the dynamics of a complex scalar field which undergoes spontaneous symmetry breaking. So as I mentioned, the tricky part of this are these strings, these topological defects. You can understand these strings in the following way. Let's look at the potential for this field. When you go in a circle around a circle which encloses a string, these strings are defined by the axion field acquiring a full 2 pi phase shift. It goes all the way around. But now let's imagine shrinking that size of the circle around the string. As you shrink the size of the circle, you still have a 2 pi phase shift. That tells you a gradient diverges when you take the size of that circle to 0, because you have a finite field excursion over an infinitesimally small amount of space. Therefore, a gradient must diverge. So this picture is axion strings are divergent. They are defects in this picture. In reality, something comes in to regulate this defect. What comes in? It's the radial mode, which comes in to regulate this defect. So in this cosmology, after you go through this phase transition, you generate the axion, you also generate this heavy radial mode. But this heavy radial mode quickly damps out to 0 everywhere in space. The axion, which is effectively massless, keeps on getting pushed around and maintains its dynamic abilities. So over here, the radial mode is 0. But at the locations of these string cores, the radial mode is restored in order to regulate this singularity. This picture is extremely hard to simulate for the following reason. These strings are defects which stretch over the scale of the cosmological horizon. Physically, they are thinner than a proton. So you need to put something on a computer which is thinner than a proton as long as the size of the universe. And that is challenging because there's a huge hierarchy of scales. And that's the main reason that progress in understanding the answer to this question has been so difficult. Really, for decades now, people have been trying to solve this since the 1980s. So we were able to make progress here by using an adaptive grid. So let me tell you how this works. here is an example of our string. What we care about, and which I'll show you more, is the axion radiation, which is emitted from these strings, because that axion radiation goes on to become the dark matter. So we use an adaptive grid, which is able to maintain high resolution around these string cores, but lower resolution elsewhere, so that we can fit more of the state into memory. We then have to still put it on some of the biggest supercomputers in the world. We use Perlmutter for this at NERSC in Berkeley, and run it for a really long time. But this helps us make a big advancement in the size of the simulations that we can perform. Here's another illustration of our grid. You can see we have a coarse grid. We have different refinement levels, which zoom in around the locations of these string cores, and we adjust these grids dynamically throughout our simulations. At the end of the day, we get pretty pictures, like this one that you're seeing here. So here you can see some of these axion strings, and you can also see the radiation that they emit during their evolution. What we care about is not the strings themselves. We care about that radiation, because that radiation becomes cold at late times and goes on to become the dark matter that we observe in this scenario. So let me show you a few animations. The first one will only show you strings. So these strings move dynamically, but the system is critically driven to an attractor solution where the number of strings per cosmological horizon is roughly constant. Here you see a cosmological horizon expanding, and if you look at this by eye, the number of strings, or the string length per box, per Hubble box, is roughly constant as a function of time. So this is just the string aspect of it. As I mentioned, we don't actually care about the strings. We care about the axion radiation that these strings emit. So now here you can see a projection, 2D projection of the strings, and you can see the radiation that they're emitting. You can see radiation coming off in shock waves. There's kinks that are formed. There's a lot of nonlinear dynamics that are going on, which are producing this axion radiation. So now let's zoom in, and we can see our different refinement levels in our lattice. So here I'm zooming in on a kink around one of these strings, and you can see here a few of our different refinement levels. And then we can zoom in even farther, and you'll see our finest refinement level right here at the string core. So we'd never be able to cover our full grid with this resolution, but through this adaptive mesh routine, we can maintain the necessary resolution that we need where we need to do it. Let me just show you one more of these simulations because I think it's pretty. Here you can see the network evaporating at the epoch of the QC phase transition. So the results of these efforts are a prediction for what the axion mass should be. And these predictions are important because they inform the experimental program. This plot has two axes. For the moment, ignore the y-axis. I will focus on the y-axis for the rest of this talk, but for the moment, let's just focus on the x-axis, which is the mass of the axion. What we find from these simulations is that the mass of the axion should be roughly around 50 to, say, 300 microelectron volts, so, or here, 40 to 300 microelectron volts. That range is an expression of our theoretical uncertainty. We should be able to shrink that uncertainty in the future, and we are actively working on shrinking this uncertainty down. But this selects a specific mass range, which tells you which experiments you should be looking for. On the other hand, these predictions are only relevant if the axion is generated after inflation. If the axion is generated before inflation, then the dark matter abundance you get is degenerate with where you happen to inflate from. And so here it's very hard to make predictions. In that cosmological scenario, you can have axions explain all of the dark matter actually over almost this entire parameter space. And in fact, some collaborators of mine, some of my students and others, we recently pointed out that this lower mass range down here is in fact more theoretically motivated coming from string theory. So if you like the string theory axion story, you should be focusing on this low mass axion part. If you like the nice predictive story of axion cosmology, you should be focusing on this upper part. Unfortunately, these two different mass ranges are completely non-overlapping, but that's the state of this field. So if you're an experimentalist listening to this, what should you do? You should ignore all of this and you should look for axions over this entire possible parameter space. But what it tells you is that if we find an axion, no matter where we find it, we will learn something. It's very confusing. There's no single point in this parameter space that makes everybody happy. No single point that makes me happy. It makes me happy for different reasons. Okay, so now let's start talking about the other axis on this parameter space. The other axis here is the axion-photon coupling. I told you that the axion-photon coupling, which now I'm labeling GA gamma gamma, is inversely proportional to this decay constant, the scale at which the axion is born. The mass is also inversely proportional to the decay constant, so the axion-photon coupling is proportional to the mass. So the axion is expected to live on this yellow line. We plot this broader parameter space because you can talk about axion-like particles which live elsewhere. These are useful to talk about when you are performing an experiment, because then you can quote your sensitivity even if you don't reach the model that we care about, which is the QCD axion which lives on this line. But when you look at these figures, you should keep in mind the only part that we truly care about is the part which hits this gold region. So these are the current constraints on the axion. Everything which is shaded a dark color is an existing constraint. So that includes this purple. This is a constraint from my group, from neutron star cooling. Axions heavier than this would overcool neutron stars. So there's a constraint right here. And then there's a theoretical constraint that tells you that axions should be more massive than 10 to the minus 12 eV. Otherwise, the decay constant would be bigger than the Planck scale. So within this roughly 10 orders of magnitude, the QCD axion can live anywhere except for this region right here where the ADMX experiment has already set a constraint. Otherwise, this parameter space is completely wide open. Everything which is lightly shaded is a projected sensitivity from a future experiment. So why should you care about axion physics right now? You should care because it's a very well-motivated model that is essentially unprobed. But this could change dramatically over the coming years if we actually invest in and do the work needed in order to search this parameter space. So now let's start transitioning to talk about what these experimental efforts are. So almost all of these efforts use the axion-photon coupling, this AE dot B. That allows an incoming axion wave to hit a magnetic field, and what will happen? Almost always, absolutely nothing, because GA gamma gamma is numerically extremely small. But every once in a while, you get a faint electromagnetic signal which comes out. Let's try to understand the frequency of this signal. So imagine this axion wave is non-relativistic, it's dark matter. So its energy is set by the mass of the axion. Energy is conserved. So the energy of the photon that comes out the other end is equal to the energy of the axion, which is equal to the mass. And the energy is related to the frequency. You combine all of these very famous relations together, and you find that the frequency is set by the mass of the axion. So then you can ask, where is this frequency? Where on the huge electromagnetic spectrum does our QCD axion mass happen to sit? And it just happens to sit in the radio and microwave range. Didn't have to be that way, but that's where it sits. So the first thing that might come to mind is the following. I told you the galaxies like our Milky Way are surrounded by dark matter. Imagine dark matter is an axion. We also know that magnetic fields permeate our galaxy. So then maybe if we look with radio telescopes up at the sky, we can start to see all of this beautiful structure that I hinted to before. And that's actually not crazy. That's something that my group has been pursuing quite a lot. Also, Catherine has thought about over the past few years. In particular, a good place to focus on is neutron stars, because neutron stars have the strongest magnetic fields out there in our universe. And indeed, we and other groups have done radio searches pointing radio telescopes at nearby neutron stars, neutron star populations in our galactic center and elsewhere. And we've already set some constraints, shown up here in green, on the QCD axion. To get those constraints down here would require future instruments. For example, we think that with a square kilometer array, we might be able to improve these enough, potentially, to probe the QCD axion. But now let me describe the experiments which have actually reached sensitivities to the QCD axion. So experiments like ADMX, Haystack, these other ones you see, they all work in the same way. And it's through the following principle. What you want to do is you put a magnetic field in the lab within a cavity. Your axion comes in, it converts into electromagnetic wave, and you match the cavity resonance frequency to the wave to the frequency of your electromagnetic signal, to the mass of the axion. Then you can resonantly enhance the signal within the cavity, and you then put in some sensor which can measure the power in your cavity. That's how these experiments work. The ideal quality factor for your cavity is 10 to the 6. And that's because the quality factor of the axion is 10 to the 6. These axions are non-relativistic only up to 1 part in 10 to the 6, because within our galaxy, dark matter is moving at a few hundred kilometers per second. So that induces an energy dispersion on the order of a few hundred kilometers per second divided by 3 times 10 to the 5 kilometers per second squared on the order of 10 to the minus 6. However, there's a Goldilocks problem, for those of you familiar with Goldilocks, happening here, because this only works if your cavity is just right. So if you're looking for a 25 microeV axion, that corresponds to a 5 centimeter cavity. It's a very human scale at which we can do experiments. But then what happens when we go outside of this range? So if we go to higher masses, the wavelength becomes smaller, you would need a smaller cavity. And then you simply don't have enough power to detect the signal. So this approach does not work at high masses. What if you go to low masses? If you go to low masses, your cavity would need to be huge, and then it's just unphysical. It could be kilometer scales, and we can't build kilometer scale cubic cavities. So beyond this region, you need other approaches to detect the QCD axion. In this region, as a theorist, I think I'm allowed to say this, we know how to do it. ADMX just needs to keep on running. Haystack needs to keep on running, and this region of parameter space can be covered. So we have ideas for how to cover these remaining parameter spaces. Let me just focus on one for 1 second. I'm not going to tell you anything about the physics. This is an idea which I was involved in proposing. Abracadabra, I can tell you more afterwards how this experiment works, which can potentially probe much of this parameter space at low masses where we expect axions to emerge in the context of string theory. After our theory proposal, this was an actual experiment at MIT, which ran successfully. Here's its upper limit at the very top. And very excitingly, just recently, our new faculty, Chiara Salemi, and we got funding for a experiment which we call CAL. It stands for CAL, Axion LC experiment. And this will be a scaled up version of Abracadabra that will take place at Berkeley, and hopefully part of a long experimental program that will make happen there, which can detect QCD axions that are predicted in string theory. But that's not what I want to talk about right now. What I want to focus on for my remaining few minutes is a new idea that we're coming up with to probe this high mass part of the parameter space. At high masses, these laboratory experiments become a little bit more challenging. It's also harder to explain axions as dark matter at very high masses. So this example is very different. This doesn't involve laboratory experiments. This is an example of how we can look for axions with supernova and gamma ray instrumentation. So this is an example that came out from my group from last year, and the exciting part of this that I want to tell you about is some new instrumentation that we've actually already started to construct. So the idea is the following. Let's talk about a core collapse supernova. What is a core collapse supernova for those of you who aren't used to thinking about this? So we have a massive star. We build up during stellar evolution an iron core within that star, and eventually that iron core will collapse under its own gravity. It will collapse until you get nuclear densities. Then you form a protoneutron star. Suddenly the collapse stops and you get a bounce outwards which explodes the star. And that's the supernova that you see in the sky. But from that protoneutron star is extremely hot, and it can produce new particles. For example, it can produce neutrinos. And indeed, after supernova 1987A, which was the last somewhat nearby supernova to take place, there was a neutrino burst observed around the world lasting around 10 seconds. So in addition to producing neutrinos, these hot protoneutron stars can also produce axions. In fact, the Feynman diagrams to produce axions are almost identical to the ones that you use to produce neutrinos, except since neutrinos are fermions, you typically have to pair produce them, whereas for axions, you can produce a single axion. So you can have two hot neutrons collide within your protoneutron star, brimming off an axion. You can have pions produce axions, and so forth. The typical energy of those axions is on the order of the temperature, and so peaking at around 100 MeV, sometimes even a little bit higher in energy, and the time duration of the signal lasts for around 10 seconds. We cannot observe axions. Axions are extremely hard to detect, but what can happen, what we pointed out last year, is that those axions can reconvert into observable gamma rays outside of the protoneutron star. All stars are surrounded by magnetic fields. Even our sun is surrounded by a magnetic field. What happens is you have the protoneutron star, which forms. The star has yet to explode within the first 10 seconds. All of these axions are produced. They propagate at the speed of light. They escape the star. When they escape the star still looks the same as it did hours earlier. They then encounter the strong magnetic fields, or the moderately strength magnetic fields, surrounding that progenitor star, and they have the opportunity to convert into gamma rays in those stellar magnetic fields. And those gamma rays we can look for then with gamma ray telescopes. And you're looking for a gamma ray burst coincident with the neutrino burst. In fact, there was a telescope in the sky studying the sun at the time of supernova 1987A, which is called the Solar Maximum Mission, and it did not observe a gamma ray burst coincident with the neutrino burst. We can use the data from that telescope to set a constraint on axions. And the constraint you get is the one shaded here. This is the constraint relevant for a particle like the QCD axion. And you can see, even with this very rudimentary gamma ray telescope from the 1980s, we're able to almost touch the QCD axion over much of its parameter space. We need to improve our sensitivity here by about an order of magnitude in order to hit the QCD axion. So we noticed this last year, and then we immediately calculated, well, what would happen today? Would we, with a modern gamma ray telescope, have the sensitivity we need to see a gamma ray burst if a supernova like supernova 1987A were to go off today? So future supernova. The galactic supernova rate, as many people here know well, is on the order of 1 per century. It's slightly better if you include nearby galaxies like the LNC, or satellites of the Milky Way. But still, it's a pretty rare event. But arguably, we're overdue if you include the nearby volume, considering that the last such event was in 1987. So what would we learn about axions from the next galactic supernova? The answer is nothing, absolutely nothing, for a very unfortunate reason. Fermi only sees about 1/10 of the sky at once. So you have an event, which realistically we can only expect one in our lifetimes. And then you have to get lucky at the level of 1 part in 10 for Fermi to be looking, which is the gamma ray telescope you should be thinking about, to be looking at the right part of the sky when this happens to take place. It's a 10-second long event. You don't have time to adjust the telescope where it's looking. If you're not looking in the right part of the sky, you miss it. But what would happen if Fermi did see the next galactic supernova? The relevant curves to be looking at are the ones here. This is our detection ability. The difference between the dashed and the dotted is irrelevant for this discussion. We would have the ability to detect QCD axions for any mass above around 10 microeV. So all of this parameter space up here, the entire parameter space that I was talking about for axions coming from strings, along with all the rest of this parameter space, we would detect or rule out an axion within 10 seconds. This is a zero background event because you have a neutrino burst, and then you're looking for gamma rays coincident with that neutrino burst. And gamma rays cannot be produced from ordinary mechanisms in that supernova since the star has yet to explode. The star still looks the exact same. The explosion doesn't hit the surface until hours later. So we have a huge opportunity for axion physics in the case of a supernova, but we are not even close to being ready because we are lacking instrumentation. So we have a proposal. The proposal is very straightforward. It is, instead of Fermi, which is overdue anyways, it is past its lifetime, to replace Fermi by a constellation of CubeSats which have 4 pi continuous coverage. So don't just launch one gamma ray telescope, launch a few gamma ray telescopes which are on different orbits to have 4 pi continuous coverage so that you're ready in the case of a galactic supernova. We call this Galaxis, stands for Galactic Axion Instrument for Supernova. And we actually received some funding from this new foundation, the PCLB Foundation, to build a prototype detector. John Tomsick at the Berkeley Space Science Laboratory is the PI of the experimental aspect of this program. And we're designing and building one of these CubeSats so that we can hopefully then build and launch a sequence of about 4 of these instruments. I should say, these telescopes would not just be useful for axions. These would be telescopes that would be targeting the hundreds of MeV range with 4 pi continuous coverage, extending all the way down in energy to about 500 keV. So for gamma ray bursts, for physics that people think about here, in conjunction with gravitational waves, having electromagnetic counterparts, this would also be the instrument that I think you would want. And there are other science applications too. So if you're interested in discussing with us and talking about what these instruments can do, please come talk to me, because we're still in the early stages of even designing these instruments. So if there's a transient signal you'd be particularly interested in, talk to us so that we can make sure that we design the instrument with that in mind. So in summary, axions are very well motivated, and I think we have a plan forward to detect them, but we need to do the work to make sure that we cover all of this parameter space. Thank you.
Thank you really for the great and amazing talk. Questions for Ben? Yeah.
Back when we were thinking about Axion dark matter in the 1980s, we made the naive guess that the Axion contribution from the misalignment would be about the same as from the Axion strings, which your simulations show was incorrect. And maybe the way to think about that is that some of the Axion energy stays locked in the strings till well after the Bechet-Quinn phase transition, so it gets released through decay to axions later and doesn't get redshifted as much. But it occurs to me that if that's right, we also guess that there would be about 1 string per horizon volume, which your simulations confirm. And can you make kind of a naive guess then of how much, of the contribution would come from the string decay without, of course, it's wonderful, the simulations you did, but can you do kind of a crude estimate that is consistent with the simulations, taking that into account?
Yeah, thank you for the question. First, also, thank you for your contributions to this field. Yeah, so let me try to answer this kind of precisely. There are 2 reasons I think that the string contribution is larger than what you and your colleagues originally expected. Although Pierre Sakivi anticipated some of this, I think. One reason is that you said we have 1 string per Hubble patch. That's what I said. I was being quick. Actually, one thing that's become kind of well established over the past few years, there's a logarithmic violation of this scaling solution. So the number of strings per Hubble patch is actually growing logarithmically as a function of time. We see that in simulations, but we also have a nice analytic understanding of that now, of why there's that logarithmic violation of scaling. What does that mean? By the time you get to the QC phase transition, which is the time you care about, the number of strings per Hubble patch is actually more like 10 to 20 instead of 1. That might seem like a small amount, but this just linearly multiplies the abundance of dark matter, which means that the abundance of dark matter from strings is 10 to 20 times larger than what it was assumed to be just from that alone in the 1980s. Then there's another aspect of this, which is how the strings radiate axions. So this is a bit more subtle, And this is the part that I think Safdi had some insight into. So what you can calculate analytically, you don't need simulations for, is how much energy the strings produce in axions, because that's just energy conservation. If the string network is maintaining some scaling solution, that energy has to go somewhere. It goes into axions. I can tell you how much energy is being produced per unit time, per unit volume, without doing a simulation. But energy is not conserved during the QCD phase transition, because QCD suddenly dumps energy into the system by turning on the mass of the axion. The thing which is almost conserved is number density. So what matters is not the energy you're producing in axions. What matters is the number of axions that you're producing. And the relationship between energy and number depends on the spectral index of the radiation that you're producing. So if all of the energy is going into very low energy modes, that will produce more number of axions than if all of the energy is going into very high energy modes. So what has to be computed by simulations is the spectral index of radiation coming off of these strings in terms of axions. That is the aspect of this in particular which is not analytically tractable at the moment. What we find in our simulations is that index to actually 0.05% precision is conformal. Safdi postulated this out of nowhere in the 1980s, that there was going to be a conformal index without a proof, without anything. We still don't have a way of proving that this spectral index should be conformal, but that's what we find from our simulations, that it's a conformal index. Given that conformal index, we can then put this in and determine this abundance. But that's the part that actually needs simulations.
Clever.
Clever Pierre, yeah.
Aside from it, can you say more about the dynamics of the strings and how things form and that kind of thing?
So I don't have very good intuition for the dynamics, other than, you play the simulation, this what happens. But at any given, so I don't know if I can provide anything too insightful to answer that question in terms of intuition behind what's going on. But let's imagine that you're maintaining a scaling solution. So what's happening? How do you maintain a scaling solution? The strings can do a variety of things. They can shrink. They can shrink by just emitting axions, which makes, by energy conservation, their size must get smaller. But they also have kinetic energy, and they can twist. And when they twist around, they form kinks. But when you form a kink, a region of large curvature, you then tend to produce a lot of axions. That's just like electromagnetic radiation or gravitational wave radiation. Whenever you put such you end up with a very large gradient or a large energy density, you tend to produce a lot of radiation. So those tend to damp away very quickly. Then these strings are moving, so sometimes they collide with other strings. And when they collide, they can do a whole bunch of different things. They can split off smaller strings, or they can form kinks on existing strings. But it's a nonlinear system, and all of these things are happening at the same time. And so I don't know if I can give any more intuition behind the fact that just these are the behaviors that are going on here.
When the QCD transition occurs, those strings should turn into membranes, right?
Yeah, great question. So this is something that I just completely neglected to mention. When this string network exists until you hit the QCD phase transition, when you hit the QCD phase transition, the axion gets a mass, which is what we were talking about before, and that mass collapses this entire network. One way of seeing how that happens is you develop domain walls or membranes between strings. So if you have a string which is some closed loop, suddenly you have a membrane or a domain wall which has its own tension, and that source of tension will be an extra force pulling this string down. So this entire thing will collapse and disappear. And actually, this last simulation that I showed but did not explain illustrates that. So this here you can actually see these domain walls form, and then the network is gone. So this is actually showing that epoch of the cosmology, which we must simulate also.
There be enough time for the shrinking of the membrane?
The shrinking occurs on the order of a Hubble time. So within roughly a factor of 2 in time of when these domain walls become relevant, the network is gone. In terms of enough time, well, then you have to ask what bad would happen. And bad things would happen if this network persisted past BBN. Because at BBN, we have precision measures of cosmology. This can definitely not be there at BBN. BBN occurs at a temperature of around an MeV. All of these dynamics occurring at around 100 MeV, the epoch of the QC phase transition. So all of this is well gone by the time you hit BBN. So unfortunately, there's no direct way in cosmology that I know of to actually probe this epoch. There are gravitational waves emitted, but they're tiny in amplitude. So we really don't have a way of directly probing this other than through the Axion remnant.
Any final question? Okay, maybe let me ask one. What do we do about the lower mass? It said that if we detect the galactic supernova, that rules out basically everything on the high end scale. What do we do about the lower end?
So the lower end is precisely what we are trying to cover at Berkeley with this this sequence of experiments building off of abracadabra called starting with this Cal experiment. Also, DM radio is going to be, well, there's a variety of experiments, abracadabra, DM radio, Cal. We are trying to cover this region of parameter space using this experiment, which I didn't actually tell you how it works, but these are essentially large volumes of magnetic fields with very sensitive pickup circuits. That should allow us to cover this entire parameter space here. I've cut this off at 10 to the minus 9 eV. Honestly, I think if we have to, we can push this down to 10 to the minus 10 eV. It's just a matter of money, scaling things up. But technologically, it's not challenging to go that extra order of magnitude. Below 10 to the minus 10 eV becomes harder. That's where the Axion happens to live. Casper is a completely different proposal for detecting axions, which uses spin precession. It uses the fact that not the coupling to electromagnetism, but if the axion removes the neutron electric dipole moment, axion dark matter actually reintroduces an oscillating neutron electric dipole moment, which is oscillating at a frequency set by the mass. And Casper tries to look for those oscillations. It's a very challenging experiment. It uses NMR technology, and I think it's something that people should work on more. But I don't want to say anything bad. It's just a challenging experiment, which has run into some issues over the past years. Below this, you have the hope of black hole superradiance, so LIGO kicking in and seeing either continuous gravitational wave signals or seeing absence of black hole spins that might be able to march down to 10 to the minus 11 eV if we're lucky in seeing low mass black holes. Depends on how low in mass the black hole mass spectrum goes, or seeing some of these continuous gravitational waves. These are our options.
Great. On that note, thanks everybody, and the PMA gathering should be happening again.